The AI models operating at the edge of modern capability hold an almost unfathomable amount of information. Systems like GPT-4 and Google's Gemini 1.5 are built on hundreds of billions, if not over a trillion parameters. Yet when you ask them a question, the response begins generating in a matter of milliseconds. They pull from that vast ocean of data with startling speed. Mathematically, this creates a strange paradox. Pushing a simple text prompt through a trillion-parameter neural network should require an astronomical amount of compute. It should be sluggish, heavy, and prohibitively expensive. The reason it works is due to a quiet architectural shift. These frontier models manage to detach total knowledge capacity from the cost of actively running them. To understand exactly how they did this, we have to look at how large language models used to be built. In 2020, the standard approach was something called a dense model. GPT-3 was a massive, dense model with 175 billion parameters. In a dense architecture, every single parameter turns on to process every word you feed it. Think about the inefficiency there. A dense model uses the exact same massive processing power to parse the simple word "the" as it does to unpack a complex biological concept like photosynthesis. Every node fires, every time. Because size and compute are locked together in a 1-to-1 ratio, scaling up becomes a trap. Doubling the model's intelligence guarantees doubling the computing power required to run a single query through it. By the early 2020s, the industry was hitting a very real physical and financial ceiling. Engineers knew that larger models would yield better results, but running them would demand a staggering, unsustainable amount of hardware. The blueprint to escape this trap was already sitting on a shelf. In 1991, MIT researchers Michael Jordan and Robert Jacobs published a paper detailing a concept called a mixture of experts architecture. Instead of one monolithic network, you divide the system into specialized subnetworks, the experts. A central gatekeeper routes incoming data to the best expert. But during training, this gatekeeper would inevitably collapse, sending all data to a single subnetwork, leaving the rest completely idle. Mixture of experts remained a beautiful theory on paper, blocked by practical instability. It waited decades for the specific hardware scale and routing logic needed to transition into the real world. That engineering arrived in January 2021. A team of researchers at Google published the switch transformer, marking the moment sparse architectures finally stabilized at scale. The breakthrough was hard routing. Instead of dividing data, the system forces each incoming token to travel to exactly one specialized expert, one switch, one destination. This strict routing successfully trained a 1.6 trillion parameter switch transformer, matching dense capability using 1/7 the computing time. Inside the network, a quiet strangeness began to unfold. Without any human instruction telling them what to learn, the distinct experts started developing distinct statistical preferences. One might lean toward syntax, another toward factual recall, entirely through emergent behavior. The results proved that sparse networks could outpace dense models at the same level of capability. This established a new scaling law. Performance no longer required a linear increase in compute. This shift materialized for the wider world in December 2023, when Mistral AI released Mixtral 8x7b. This model pulled the architecture out from behind closed corporate doors and dropped it directly into the open source community. Looking closely at Mixtral reveals the exact mechanics of this decoupling. The model holds 46.7 billion total parameters. But because it relies on specialized routing, it only activates roughly 12.9 billion parameters to process any single piece of data. Testing showed that this highly selective model matched or even exceeded the benchmark set by massive systems like GPT 3.5, all while demanding drastically less hardware to operate. Mixtral proved that selective activation was a tangible, deployable reality. It validated the sparse architecture for developers globally. This explains the modern AI landscape. The industry-leading models setting the frontier on capability, GPT-4 and Gemini, achieved their dominance because they operate as highly complex sparse models, activating only a tiny fraction of themselves at any given moment. The very definition of model size has changed. The limiting factor is no longer the raw, brute force computing power required for a single pass. It is now about how many specialized experts a system can afford to maintain. Researchers are focusing their energy on perfecting the elegant routing mechanisms that connect these experts together, rather than blindly expanding a monolithic core. This architectural shift suggests that massive scale is best achieved not through uniform brute force processing, but through the strategy of learning exactly when and how to be selectively brilliant.